April 10th, 1815, Indonesia. On this day, history witnessed one of the most cataclysmic natural disasters ever recorded. Tens of thousands of lives were lost. Millions of tons of ash were blasted into the atmosphere, choking the sky and blocking out the sun. It was an event so severe that it turned 1816 into the year without a summer. Now, we tend to view volcanoes purely as symbols of destruction and devastation. But in reality, they are actually a crucial component of the Earth's life support system and have been for billions of years. Back in the early 19th century, no one truly understood how our planet formed or how it functioned. Humanity had just witnessed a disaster that altered the global climate, yet they were completely powerless to explain its origins. Where exactly did this destructive power come from? The prevailing theory at the time suggested that Earth began as a molten sphere. As it cooled, its surface supposedly wrinkled, much like a dried apple. People believed that these giant wrinkles were responsible for creating mountain ranges and valleys. However, reality painted a very different picture. You see, if the Earth's crust had truly shrunk randomly like a drying fruit, then mountains and volcanoes should be distributed randomly and evenly across the planet. But they aren't. They are concentrated in specific zones. Vast areas like the centers of continents are almost entirely devoid of mountains, earthquakes, or volcanoes. Clearly, this early belief was fundamentally flawed. The dried apple theory also assumed that the Earth's crust was a solid, immovable, and eternal block of rock. This misconception caused scientists to overlook some vital clues. As early as the 16th century, Dutch cartographers like Abraham Ortelius noticed a strange coincidence. The western coast of Africa and the eastern coast of South America seemed to fit together perfectly, like pieces of a giant jigsaw puzzle. But without practical evidence, this observation was largely ignored. It wasn't until 3 centuries later that a visionary mind revisited this mystery. Alfred Wegener, a German meteorologist. In 1915, he proposed a revolutionary theory. Wegener suggested that all modern continents were once united in a single supercontinent, which he called Pangaea. Over time, this massive landmass broke apart and the fragments drifted to become the continents we know today. This time, Wegener's idea wasn't just a hypothesis on paper. It was backed by compelling evidence. First, there was the undeniable fit of the South American and African coastlines, the very anomaly Ortelius had spotted centuries prior. Second, the fossil record. Scientists found fossils of the Mesosaurus, a creature extinct since the Permian period, in both Brazil and southern Africa. Similarly, fossils of the Glossopteris plant were discovered across India, Australia, South Africa, and even Antarctica. Third, geological similarities. The Appalachian Mountains in North America shared the same age and structure as the Caledonides in Europe. They could only align so perfectly if they had once sat side by side, sharing the same climate and conditions. And finally, the most damning piece of evidence came from the frozen wasteland of Antarctica. Explorer Robert Scott discovered fossils of tropical rainforests buried deep under the Antarctic ice. This proved that this frozen continent once enjoyed a warm, wet climate, much like our modern-day equator. Wegener presented his theory to the public with absolute confidence, yet it was ultimately rejected. The problem wasn't his evidence, it was the mechanism. He couldn't explain how massive continents could plow through the ocean floor. Wegener suggested forces like the Earth's rotation or tidal pull, but physicists quickly proved these were far too weak to move entire continents. To the geologists of his time, continental drift was absurd. Wegener was ridiculed, and his theory faded into obscurity, seemingly buried along with him when he died in 1930. But the scientific community had missed something crucial. Wegener didn't lack evidence. He lacked the technology to see what was happening beneath the ocean's surface. Fast forward to the 1960s. A global network of seismometers was established, allowing scientists to pinpoint the exact origins of earthquakes. The results were astonishing. Earthquakes didn't happen randomly. Instead, they traced narrow bands across the planet. These bands defined the boundaries of tectonic plates. Furthermore, by studying the magnetic orientation of the seafloor, scientists discovered magnetic striping that mirrored perfectly on both sides of mid-ocean ridges. This was the smoking gun. The Earth's crust was being continuously created and pushed outward. Finally, we understood how the plates moved. The Earth's crust is less dense than the hot, molten mantle beneath it, allowing it to float. But not all crust is created equal. Continental plates are less dense than oceanic plates, which allows them to pile up into massive mountain ranges that float high above the surface. When two plates of similar density collide, neither sinks. Instead, the immense pressure forces them to buckle and break, creating towering ranges like the Himalayas. However, if plates of different densities collide, the heavier one is forced down, subducting into the mantle. As this rock sinks, it heats up, melts, and releases water and minerals, generating vast amounts of magma. It is this magma that fuels explosive eruptions, like the one at Tambora. The immense energy generated by tectonic activity explains the destructive power of volcanoes. But interestingly, volcanoes also play a pivotal role in nurturing life. Why? The answer lies in the carbon cycle. This is the process that moves carbon between the atmosphere, the land, the ocean, and living things over millions of years. And volcanoes are both the beginning and the end of this cycle. Imagine the Earth entering an ice age. Low temperatures slow down the weathering of rocks, reducing the amount of CO2 absorbed from the atmosphere. But volcanoes, they don't stop. They keep pumping CO2 from deep underground into the air. This accumulated CO2 acts like a thermal blanket, trapping heat and warming the planet, helping life survive the deep freeze. Conversely, if the Earth gets too hot, the cycle self-corrects. High atmospheric CO2 leads to more acidic rain. This rain erodes rocks, releasing ions like calcium and bicarbonate, which flow into the ocean. There, marine life, plankton, corals, and mollusks use these ingredients to build their shells and skeletons out of calcium carbonate. This is how carbon is locked away. When these creatures die, they sink to the seafloor. Over millions of years, these layers of sediment are buried, compressed, and cemented into rock, storing the carbon safely away, resetting the balance. Eventually, these remains transform into limestone, a rock incredibly rich in carbon. This continuous process creates massive carbon reservoirs on the ocean floor. In essence, the ocean and its marine life act as a giant vacuum cleaner, sucking CO2 out of the atmosphere and helping to cool the planet down. But here is the catch. If the cycle stopped here, all the CO2 in the air would eventually be locked away in stone, and Earth would freeze over permanently. This is where plate tectonics proves its irreplaceable value. It carries these rock layers deep into the mantle, melting them down and releasing that trapped CO2 back into the atmosphere through volcanic vents, just like the eruptions we discussed earlier. Thanks to this process, the carbon buried in the rock is recycled, beginning the journey all over again. And so, this magnificent cycle acts as a natural thermostat, maintaining Earth's temperature stability for millions of years. But what happens if this perfect balance is broken? To find the answer, we only need to look at our neighbors, Venus and Mars. Initially, Venus was thought to be Earth's twin. It has a similar size, and it once possessed liquid water and an atmosphere. Its volcanic activity was also intense, constantly pumping CO2 into the air. However, Venus lacked Earth's balancing mechanism, specifically oceans and life, to absorb that carbon and lock it into rock. The consequence was catastrophic. As CO2 levels skyrocketed, the atmosphere thickened, triggering a runaway greenhouse effect. Temperatures soared, causing the oceans to evaporate. This massive amount of water vapor became yet another powerful greenhouse gas, trapping even more heat. The intense heat prevented water from condensing back into liquid, completely halting the weathering process. As temperatures climbed even higher, water vapor rose into the upper atmosphere. There, unprotected, it was exposed to direct ultraviolet UV radiation from the sun. This intense energy shattered the chemical bonds of water molecules, ripping them apart into hydrogen and oxygen. Because hydrogen is so light, it was easily blown away into space by the solar wind. The oxygen, being heavier, was left behind to react with the surface rocks. This process stripped Venus of its water entirely. Today, Venus has an atmosphere 90 times thicker than Earth's, composed of 96.5% carbon dioxide. Its surface is shrouded in thick clouds of sulfuric acid, with temperatures exceeding 450 degrees, hot enough to melt lead. It is a literal hell, all because it lacked an effective mechanism to recycle carbon. In stark contrast, Mars suffered the opposite fate. Because it is much smaller than Earth, it cooled down significantly faster. Its core was no longer hot enough to drive plate tectonics or sustain long-term volcanic activity. As volcanoes went dormant, the supply of CO2 to the atmosphere dwindled. Like Venus, Mars once had a primitive carbon cycle. Liquid water weathered the rocks, locking some CO2 into sedimentary layers. But when the volcanoes stopped, there was no mechanism to unlock it and release it back into the air. The imbalance worsened because Mars lacks a protective magnetic field. Without it, the solar wind stripped away most of the planet's atmosphere, carrying off the little CO2 that remained. As the thermal blanket thinned, temperatures on Mars plummeted. The remaining atmospheric CO2 froze at the poles as dry ice. Mars lost its greenhouse effect and became a frozen, dead world, with average temperatures dropping below -60°C. Through the tragic fates of our neighbors, we can truly appreciate the precision and perfection of Earth. The carbon cycle and plate tectonics work together like a colossal machine, regulating the atmosphere to keep temperatures stable. This balance isn't an accident. It is the result of billions of years of geological evolution. It is this unique combination that makes Earth the only known oasis of life in the universe. But that is not all. Volcanoes do more than just sustain life. They help build the very environments where life begins. Billions of years ago, Earth was a hostile place, constantly bombarded by meteorites and asteroids. Volcanic eruptions occurred on a scale far greater than anything we see today. Water vapor, carbon dioxide, nitrogen, methane, and ammonia were released from deep within the Earth, forming the primordial atmosphere. As Earth cooled, the water vapor began to condense. Because the volume of steam was so immense, it rained continuously for eons. This deluge filled the lowlands, creating the first oceans. These ancient oceans weren't just water. They were a primordial soup, rich in chemicals from volcanic activity. Here, lightning and UV radiation interacted with molecules to produce complex organic compounds, the precursors to life. One of the most magical environments created by geological activity is found deep on the ocean floor. Hydrothermal vents. These are oases of life existing in perpetual darkness. Here, cold seawater seeps down into cracks in the Earth's crust. When it meets magma at depths of 2 to 3 kilometers, the water is superheated to over 400 degrees Celsius, dissolving minerals like sulfur, iron, zinc, and copper from the surrounding rock. This mineral-rich, superheated water then erupts back into the ocean, forming chimneys that spew black or white smoke. Unlike ecosystems on land that rely on the sun for photosynthesis, life here is completely independent of light. Bacteria and single-celled organisms use a process called chemosynthesis to generate energy. They thrive on the chemical reactions of the minerals spewing from the vents, specifically hydrogen sulfide, methane, and iron. These bacteria form the base of a complex food web, supporting bizarre and unique creatures. Many scientists believe these hydrothermal vents were the cradle of life on Earth. The environment here is incredibly stable, providing a constant source of energy and chemicals. More importantly, it was protected from surface threats like intense solar radiation and the frequent meteorite impacts of the early solar system. Volcanic activity also provided the essential building blocks for biological molecules. Take phosphorus, for example. It is a critical component of DNA and RNA, as well as ATP, the molecule that carries energy in cells. Originally, most phosphorus was locked in rock, weathering too slowly to be useful. But volcanoes brought phosphorus-rich rocks from deep underground to the surface, where they could dissolve into water and fuel the rise of life. They also supplied essential trace metals like iron, zinc, and copper, which are vital for enzymes and metabolism. So you see, volcanoes and plate tectonics saved Earth from becoming a hellscape like Venus or a frozen wasteland like Mars. They didn't just shape our atmosphere and oceans. They provided the essential ingredients to build the very first life forms. Volcanoes, often feared for their destructive power, are actually the key that unlock the door to life. They are not the end, but the most powerful beginning, transforming a barren rock into a vibrant, living world.